Hi everyone, my name is Nour Fahmy, and welcome to our talk today. We are part of AISC, which is a ML repository. You can find us at AI.SCIENCE, and today we are delighted to present Kamil, Adamczewski, and Mujung Park, who are working at ETH Zurich and Max Planck Institute. So without further ado, Kamil, please start us off.
Good day, everyone. Hi, Nour. Thank you very much for your invitation. Thank you for having me here and the introduction. Can you see me?
I can see.
I see myself. Yeah, okay. All right. Okay, can you see my screen? Can you see everything that you need to see?
Yeah.
Okay, great. Okay, so once again, hello everyone. Thank you for having me here. And today I will be talking about my new paper, which I co-authored with my supervisor, Mujung Park, on Dirichlet pruning for neural network compression. I try to keep this presentation as accessible as possible towards the wider audience. So if things are too easy, please bear with me, please be patient. And if there's anything unclear, feel free to ask me at the Q&A at the end. Okay, so without further ado, you perhaps are familiar from what I know with the topic of neural network compression. Nevertheless, I just make a brief introduction. Convolutional neural networks have increased in size from the LeNet architectures in 80s, 90s to the current large architecture. They become bigger and wider, and of course they also become more accurate. But the fact that they are getting bigger also comes at the cost. So there are certain explicit costs which you have probably heard. Large networks take more computational time and more memory. It's more difficult to run them on hardware-limited devices such as smartphones, robots, in autonomous driving. Sending millions of parameters through the limited network is costly, and not mentioning energy costs of training those networks and possibly overfitting. However, except for the explicit costs, there are also implicit costs of those large architectures. So adding additional layers and kernels, given that we have better and better hardware, costs relatively little. So we can keep adding them without little thinking why we're doing this. So we focus rather on quantity and not on the quality. In neural networks, feature selection doesn't really exist because that's the network what is learning the features. So ironically, this trend opposes the research about the nature, interpretability, and knowledge extraction from within the neural networks. Nour, did you? Yes.
When you say additional layers and kernels cost relatively little, what do you mean by that?
Well, I mean that given the fact that we have stronger GPUs and we have parallel computation, basically it is relatively easy to create networks which are large right now compared to what was before when the large architectures were prohibitive. So that is basically what I mean, that by adding an additional layers is relatively little, relatively easy.
I got you.
Okay. So this work is part of the pruning network pruning literature line of work. And what is pruning? Pruning is a neural network compression technique. It's one of the neural network compression techniques, along with, for instance, low-rank approximation, knowledge distillation, quantization. But pruning has become recently quite popular because of its applicability and its practicality, which can be easily implemented. So pruning is basically removing connections from the neural network. We can remove neurons, which are those circles, nodes on the picture, or we can remove synapses, which are the connections weights. In this work, we are focusing on the case where we are removing the entire neurons. And please notice that if we remove a neuron, we will immediately remove the incoming and outgoing connections, making the network slimmer and smaller. Here on the picture, it's an example of a fully connected feed-forward network. But to give you a bit more intuition about how it works for the convolutional network, let's have a look at this figure. So basically, and each node each neuron is a channel in the convolutional neural network, which is an example is the red rectangle, the vertical rectangle. Also, it could be a horizontal rectangle. So, for instance, here is a layer from VGG, the first convolutional layer, where we have 3 input channels, RGB, which all of us are familiar with, and we have 64 output channels. So, so each channel is a neuron, and each connection here is a single filter. I hope you can see my arrow. So this would be a connection in a fully connected layer, but in the convolutional layer, it's a filter. And there are different ways of pruning. What we're doing here is so-called structured pruning, where we will remove the entire channels. This is the most practical setting because removing them allows us to directly create this architecture and deploy it on in our system. There are also unstructured approaches where we, for instance, remove the connections. We remove the connections, or just remove the filters. And that is not so practical because given current implementation, current hardware, that would not lead us to smaller or faster models. But it's also an interesting theoretical issue. So this is so-called channel pruning. In the literature also you can find the name filter pruning, which I don't really like, because originally filters are the 3x3 kernels, also they are called. So calling a filter pruning may be a little bit misleading. 3D filter pruning would be a better name, or channel pruning. It's I think the clearest term, so we will stick with this term. So as I mentioned before, currently the networks are getting bigger and bigger. They're getting deeper and deeper, and that is why we have deep learning, and that is why the models are better and better. However, those deeper architecture also become wider. And here the link between the network expressivity and the width of the architecture is more tenuous. And that's what we're exploring in this work. We are keeping the height, the depth of the neural network. However, we will make the architectures thinner. So we will remove some of the channels from the network. And without further ado, how do we do it? We introduce a new operation called an important switch. In a regular neural network, we have a set of weights, set of parameters, and then we have an input. And then we multiply them, and then we get a pre-activation, which further undergoes activation, batch norm, and dropout, and whatever you want. We add another component to the architecture, which is called an importance switch. It's a vector of the importance value, and the size is equal to the output dimension of the layer. So if the layer has k parameters, k channels, excuse me, then the importance switch will have k dimensions. And then we are multiplying this vector, this importance switch, with the pre-activation, and that's how we are getting the output, which further follows the usual course, activations and dropout, batch norm, etc. So this is this little modification, and this importance switch will basically tell us how important each of the channels is. This is importance switch is more of a general concept, which we introduced with Mijong. We have another work, which is just a quick digression, which if you're interested in this line of work, you may have a look, where we generalized it to a general feature selection, because in network pruning, we are actually considering the channels as features. Here we are generalizing it to all sorts of features, input features, and we look at two ways of feature selection, global and local. Just please have a look if you're interested. However, let's go back to our work. So we know now what is an importance switch vector, and the question is now, what form does it take? And that's where the Dirichlet distribution comes into play. I will first briefly introduce the Dirichlet distribution, because understanding is important to how basically pruning happens during training. So Dirichlet distribution is a multivariate probability distribution with a positive value parameter. So the number of variables, the number of the dimension is equal to the number of parameters. They are positive. And the Dirichlet distribution is also a conjugate prior for a multinomial or categorical distribution. To give an example of Dirichlet distribution, a few Dirichlet distributions, here are 4 trivariate Dirichlet distributions. So we have three variables, and you can see how the samples from the Dirichlet distribution are distributed given what parameters we assign to those Dirichlet parameters. So if in the case of a uniform parameters all equal to 1, we will have a more of a uniform distribution across different possible categorical distributions, because what basically each black dot is a one categorical distribution which is drawn from a Dirichlet distribution. In the case when they are the same but the value is bigger, for instance 10, they will be more concentrated in the middle, which means that that each sample, the values in each sample will be more similar. For instance, 0.3, 0.3, 0.3. And that is actually what we don't want in pruning, because we want each component, some of the components to describe important neurons. That means that have higher probability, and some of them have lower. So what we would like to see is what we see in the C and D. In the case of D, we have also they also take the same values, but the distributions are more scattered. So there will be what I said before, that there will be some of the values will be higher, closer to 1, and some of them will be lower, closer to 0. The sum has to be equal to 1. And the C is the asymmetric case where basically they are all different. And that is also what we want in case of network pruning.
Can I also just a curious question about Dirichlet distribution just in general?
Yeah.
So I think that there's kind of a pattern here. The smaller the parameter, the more scattered they are, and then the bigger the uniform distribution for the parameters, the more centered they are around the center.
Yeah.
Yep.
That's right. That's precisely how it is. Yeah, it's Dirichlet distribution is a very universal distribution. If you are familiar with the beta distribution, it's a generalization of the beta distribution for a multivariate case. And this is basically our case, because we have several channels in the beta distribution. There are only 2. It's a prior distribution, so those values alpha can be also kind of it's not a precise definition, but they are also considered pre-counts, but they are not really counts because they are not integers, but that can be kind of a interpretation.
I understand. So to relate this back to the importance switch, we want the values to be as scattered as possible, so then we can pick the most important ones or the largest values.
Exactly. So that's what we want. And how do we actually learn those values? So we kind of right now understand what the vector should look like, but how do we actually get the exact distribution? We learn it, and that is kind of a neat approach about this pruning method, because we will actually learn those values. There are other methods in network pruning. For instance, they take a magnitude of the weights, and it works also well, but it's sort of a proxy for what we want. Here we will directly learn which channels are important for the network, and how we. Yes. Is there a question?
Yeah. Can you very briefly explain what the Kullback-Leibler divergence is for people who aren't familiar with it?
Yes. So I will briefly explain how variational inference works. So it's a method of inference. So we want to find a probability distribution. We want to infer a probability distribution But basically it's there's no analytical way there. We don't know exactly what form this distribution is. So what we do is we choose a distribution that we know, and we will try to minimize the difference between the two. And that is the case here. The P is a distribution that we want to learn. This is the distribution that this is the kind of unknown ground truth of the probability values of the important values of each channel. But we will model it as a Dirichlet distribution. We will give it a specified form, and then we will try to minimize the difference between these two probability distributions. And Kamil divergence is basically a way to minimize this difference. It's a formula to minimize the distance between the two probability distributions. So P is the original one. Q is so-called it's a variational approximation to the posterior distribution, which takes the form of the Dirichlet distribution. I'll talk about it in a second. And we are trying to minimize it. And so the equation 1 is actually equivalent to equation 2. After a few transformations, we will get the equation 2. And equation 2 is so-called in the literature evidence lower bound. And this becomes our loss function. And that is what we are using to optimize and to find the switch vector. And was that clear? Is there any question regarding that?
Yeah.
It was a very brief go through variational inference, but it's a very powerful technique. Another technique is called, which is often used, is MCMC. But here we used variational inference. Hello? Okay. So for this variational inference, we have to choose the prior and posterior. Prior is this P, Q is this approximation to the posterior. And as you probably already guessed, both of these distributions take the form of Dirichlet distribution. And the first one is the prior, and basically it's just it's a distribution which, if we have any a priori knowledge about the distribution, we would basically specify to have it a special form. If we, for instance, we could use a symmetric distribution, but with maybe a smaller values, so that the vector has some bigger and smaller values. In a similar way, posterior is actually what we are learning. And in this case, we want to learn the asymmetric Dirichlet distribution. And these are the parameters which we are learning during this inference. So we model them as Dirichlet distribution, and then we are learning them. One more thing, which I'm not going to talk about here, but if you're interested, you can look in the paper. It's actually not straightforward to find gradients, because we have given certain laws, we would like to compute the gradients of the parameters. It is not so straightforward. We had to do some reparametrization. If you're interested, please have a look at the paper. Yeah, or you can see later the code as well, how it works. So so why do we choose Dirichlet distribution? Again, to kind of have a clarity on that. So a sample from the Dirichlet distribution is a probability vector, which can model the relative importance of each channel. So we have the probability vector, we have the relative importance. Careful choice of this Dirichlet prior can encourage sparsity of the network. So if we basically, during the optimization, we will try to force the network to have to drive some of the values to 0, then we will be able to obtain this sparsity that we want. And we have this efficient Bayesian optimization thanks to the closed form expression of the KLA divergence. So this is our loss function, and basically, this element on the right-hand side is the Kale divergence, and this one we can actually compute analytically. So we can have a formula given the fact that we chose both P and Q to be Dirichlet. This is important because for instance, the side on the left, we have to sample. So if we sample, we have certain variance, we have certain inaccuracies, and that is what we are avoiding by having an analytical expression of the Kale divergence on the right. So that makes optimization basically better, given that we know what the Kale divergence between the two Dirichlet distributions is. So those are the reasons why we chose Dirichlet distribution. Okay, so let us look at the algorithm overall, how it works. Because we look at certain elements, and now maybe let's put it all together into one algorithm. So what we require is that we require a pre-trained model. And then we will find the importance of the channels from this pre-trained model, and that becomes the base for our final model, which is a compressed model, and that is what we ensure. This model will be a smaller, slimmer version of the pre-trained model. And how do we achieve it? So first, we add the importance switches to the architecture, one switch per layer. Then we will actually freeze the parameters of the network, except for the importance switch parameters. And then we will perform the variational inference optimization, where we will learn the importance switches. And afterwards, after we learn those importance switches, we will remove those channels which are with the values close to 0, with the small values. And finally, we will fine-tune the model with the remaining channels. When we are removing certain channels, we have certain loss in accuracy, and we want to kind of regain this accuracy back by fine-tuning the model again. So that's the entire algorithm. That's the overview of the Dirichlet pruning. Are there any questions of that? If not, I will move to just a few experiments. I will show some results.
For sure. We've still got plenty of time.
All right. Great. So some experimental results. I want to first show some visual results, which I think they are quite interesting to the audience, and they are ones which we can all relate to. One of the reasons for this work is to basically see also what the network is learning, what the network deems important. And here is an extended version of what you saw in the beginning. This is a complete feature map of the first convolutional layer of the VGG trained on cipher for one image, the image of a boat. And so these are all 64 output channels. And these are the channels which the network found important, the Dirichlet pruning found important. So after learning the important switch vector, those are the values with the highest probability, highest importance. And it's quite interesting to see, because they are somehow correlating to what, maybe not exactly, but there is a certain relation with what we would consider important. That happens because actually those important channels have parts which are have high activation values. So as you can see, the red regions, the red pixels correspond to the higher activation values, and that is actually what the network wants during the learning, and that's what it finds important. So I find it quite interesting that we can actually see these channels, and then we can actually interpret them in a way. The first convolutional network is easier to interpret. The further are quite harder. Here are a few more examples. Again, this is more of a flavor. there is no rigorous explanation, but more of a flavor, so that we see as actually what the network, what channels network find important. For instance, here are the examples from MNIST and Fashion MNIST, and you can see that the more important channels are actually denser, with kind of denser features, and the ones there's one which I here included. Those are arguably they are a bit weaker, maybe a bit jagged. They lack of focus. So it's not a general rule, but you can see a certain correspondence with what we would find important. For instance, a sole here for the shoe. That's something which describes a shoe. Yeah, so that's the visual interpretability, and also the important part for us is to create the compressed models. We perform the compression and compared with a number of state-of-the-art methods. We compare them in terms of parameters, which is the size of the model, and the flops, which are floating point operations, which is the proxy for the speed of the network, and basically the fewer the better. We performed experiments on several networks on the LANet. We're doing very well. Here there are basically, I will just briefly mention that we have three types of the algorithm. One is where we are actually, I mentioned during optimization, we optimize here. Where is it? Okay, so this is an integral. So in order to compute it, we have to actually sample. We have to sample the important switches. So we did a few variants of this optimization. One is where we are actually sampling the switches. One is where we are using actually analytic mean of the Dirichlet distribution, and another one is also where so these two are actually learning the important switches layer by layer, and this one is learning all the switches, all the ones for the entire network. So there are a few variants. If you're interested, please have a look at the paper. Here are some results for the VGG. The method does very well, I would say, in particular in terms of the number of parameters, in terms of the compression rate. And here are more examples about for ResNet and for WideResNet. Again, I think very good compression rates. Yes, and basically that's more or less it. So in summary, we have proposed a simple, light, and easy to implement approach to network pruning. It is based on probabilistic modeling in using Dirichlet distributions. And this method offers practical speedups and cutting-edge compression results. So thank you. Here are some references from the paper, and thank you very much. The code is available at my GitHub. I keep improving it, and I keep debugging it as well. So please just keep checking for newer versions also. Yeah, thank you very much.
Thank you, Kamil. We actually have some great questions from the audience if you're ready to take them.
Yes, please, let's hear.
Perfect. So the first one comes from Sergio Garrido. What is the intuition of doing the product with the important switch before and not after the activation?
Good question. We could also try that to do it after activation. We haven't tried it. The intuition would be that during the activation, we basically we lose certain information, because if we take, for instance, ReLU, then some of the values will go to 0. And well, that's I mean, to be honest, actually that should not matter right now when I think about it, because the values should be positive, and when we are multiplying it with the negative values, then they will still stay negative. So so I think that probably would not matter actually whether we do it pre or after activation. We just implemented it in this way that we do it pre-activation. But yeah, I think it should not matter actually, at least in theory.
Well, that ties in really nicely to the next question. If there is indeed, if the choice of optimizer can change anything at all. So that in particular, what would happen if you explore the sensitivity of the choice of being close to 0 at the posterior?
So if I understand it correctly, the question is whether the choice of the optimizer would determine that maybe some of the values would be further out from 0 or closer to 0, depending on the optimizer. I think well, I mean, if we want to believe that we modeled and we are basically learning the distribution, which is the true distribution. I think the choice of the optimizer should not matter. As I mentioned before, there are other ways to infer a probability distribution, for instance, MCMC. Variational inference is very popular because it has a lower variance, and I guess that's what we probably would like to have, because if the thing is that if basically some of the smaller values are close to, basically if we group the channels between those that end up with values close to 0 and the values which have basically close to 1 or just bigger values, then basically the small differences maybe in these values should not matter at the end, actually, now when I think of it. So I think the choice of the optimizer should not really matter, but we didn't try different optimizers, but this one works very well, I would say.
Awesome. So this also ties into, like, there were two parts to that question.
Excuse me, Nour, I don't know if Mijung is there. Hi, if Mijung is there and she would like to maybe chip in.
Yeah, I'm listening. I mean, your answers are good. Yes. So
okay.
I thought, the previous question was more or less, is optimization more or less stable or not? Does it matter where you start the optimization? Initialization matters or optimizer matters or something like that. And from our experience, I would say these things don't matter so much. And then the optimization was relatively stable.
Okay, very cool.
Yeah.
And then I guess the second part to that question would be, have you explored the sensitivity to the choice of being close to 0 of the posterior?
I tried to answer this question. Did I not answer it?
I think you have. Yeah.
Okay.
Cool. So another question that we have.
If I didn't, feel free to ask again later. Yeah. Go ahead, Nour.
For sure. Yes. If the audience had any leftover questions from that, then I'll definitely float them. We have another question from Alexei Propakov. Can the methods be applied to transformers-based architectures?
That's a good question. I'm not, to be honest, that familiar with the transformers. to be honest, I'm not that familiar to answer this question, and I believe they could be, because in a sense, what for instance, this method works pretty much regardless of the type of the layer that we are using, because it works. I mostly focus here on the convolutional layers. It works well also for the fully connected layers, and basically we have a set of features where we want to make a choice of which ones are more important, which ones are less important. Then it can be applied. It basically has a very wide applicability to where we want to. If we can basically phrase a problem in terms of feature selection, we can actually apply this method. So, for instance, these days I'm trying to apply this method to LiDAR, actually, in autonomous driving, where we have certain lines in LiDAR, and then we are trying to find the important lines. So, like as I said, it has wide applicability, and I think it could be also applied to the transformers. I didn't try them, and feel free to write to me, and I'd be very happy actually to look at this.
That's very, very cool. I'll definitely ask you about the lighter pruning about that a little bit too as well. We've got another question, and it's: have you tried / is it possible to train the model and the pruning jointly?
Say again. Could you repeat it again?
Yeah. Is it possible to train the model and also prune it jointly?
Yeah, it's a very good question. So our method actually works as a post-processing technique, where we will take a pre-trained model, we will prune it, and then we will retrain it. It's a kind of a common pipeline, and in this pipeline we will do it separately. There are some other methods. In particular, they are based on Bayesian neural networks. There are, if you're interested, for instance, there's another paper of mine and Mijung, which is called RDP, radial and directional posteriors. And in that work, we are actually learning the importance of each neuron during the training using Bayesian neural networks. And this is also an interesting approach, because it's all done at the same time. However, this optimization is actually quite long. It's due to the fact that Bayesian neural networks are quite hard to optimize, but then during the training, basically, pruning happens. There are other works, Bayesian compression for deep learning by Louises, and there are a few other works which do exactly what you're asking. In this work, we're doing it separately.
Very cool. And we've got one last question. Is there any interesting structures appearing in the connectivity of the leftover units, and how does it evolve during pruning?
Are there any interesting structures?
Is there a pattern that you noticed with the number of channels that are left over?
You know, it's a good question, and that's something that actually I would like to explore maybe in further work. For instance, a good question is that when we have a certain number of channels, whether we want to prune more channels from the earlier layers or from the later layers. From my experience, I noticed that actually the earlier layers seem to be more sensitive to pruning. So if we prune earlier layers too much, then even if we have later more layers, that will actually cause deterioration in accuracy. So we probably would like to prune more the later layers and keep the earlier layers less pruned. That's kind of so far my experience, empirical experience.
That's an interesting observation because it also ties into what you were showing us with the feature map earlier, where the earlier channels had a more discernible image. I wonder.
Yeah, I mean, I think it sort of makes sense because the Yoshua Bengio he advocates this kind of like feature hierarchy. So in the earlier layers we are learning those basic layers, basic features which are important for building the features in the subsequent layers. So if we remove too many of them, then actually we will have nothing to build on in the subsequent layers. So I think it kind of makes sense, but there's still a lot to learn.
Awesome. And I promise this is the last and final question. Even though I said the last one was, apart from the impact of the model, can there also be unintended impacts on other importance metrics such as adversarial robustness?
Very good issue. In my work, I actually did try a problem along those lines where I was trying to check whether the features that actually are remaining would be maybe features which are more robust or less robust, and for the adversarial attacks. And unfortunately, it turned out that at least I didn't find a connection between the features which remained and the robustness for adversarial attacks. I mean, I wish that were the case, because I mean, it would be. I mean, in theory, I mean, what I said about the features having some kind of visual explanation, it intuitively it would make sense that those are the features which are robust, because those are the features which we find basically distinguishing for different classes. But that was not the case actually. So there's something. I mean, you know, it's the whole literature, but there's something else in there which we need to find.
Awesome. So that was all the questions for today. I want to thank you, Kamil Mijung, for the great presentation. I want to thank you guys, the audience, for joining us today. And if you guys would like to see more free content like this, visit AI.SCIENCE and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. Thanks, guys, and have a good one.
Have a good day, everyone. Thank you.